Hello everybody. Now we are gonna talk about the second case of unsteady state molecular diffusion, which is the case of diffusion in a finite medium. And this case is, or this the numerical, or it's not numerical, the analytical solution of this method or of this case is more complicated than the case of semi-infinite medium. And it's mainly due to the boundary conditions. The idea of having semi-infinite medium and having one boundary condition as z equals infinity, this makes the solution much more simpler than having this as a constant value. And that's why we're not going to go through this analytical solution, but we're going to go through, we are going to use some charts that can be used to provide the solution. What we're gonna do is first talk about the cases that we can use or can be solved using these charts, and explore what are the inputs that we need to give to the charts and what are the outputs that we expect from them. So let's say, or let's first talk about the equation. So the equation has to be Fick's second law equation, or the system has to follow or to be described by Fick's second law for the finite medium, because of the simplicity of this case. More complex cases will not be possible to be solved using the charts. There are some restrictions to the use of these charts, which are related to the boundary conditions, in addition to the equation, the boundary conditions. And the shapes or the geometries that we can solve using this or using these charts. We have charts for three different shapes: for flat slab, which is something like this; for sphere; and for a long cylinder. So these are the three shapes that we can find solution to in these charts. And these charts are not put in the units of concentration, time, and distance. It's put in dimensionless forms. And this dimensionless form is very, very important, because let's say you have two cylinders. One has a diameter of 1 centimeter and the other has diameter of 1 meter. So if you put the dimensions, then the chart must have a very, very large scale to accommodate all the dimensions. But if you put it in a dimensionless form, it's gonna limit the dimensions from 0 to 1, as we will see later. And the same for the concentration, will have value from 0 to 1, and this is independent on the shape of the system, or I mean the dimensions of the system, or the value of the concentration that you're using. So this makes the chart more universal, easy to use for any dimensions and for any concentrations for any time, and this makes the dealing with the chart more convenient for different cases. So what we will do now, or before we proceed, the solution to any problem like this is, as we did in the semi-infinite medium, we ended up with an equation where we provide the temperature, we provide the location, and it gives us the concentration. This is what we do. So the chart is the same thing. It enables us to provide the time in a dimensionless form, and provide the location in a dimensionless form, and it provides or it can give us the concentration in a dimensionless form. So it's still a relation, but in a different form. The equation is one form of the relation, and the chart is another form of the relation. And now back to the equation for Fick's second law. Again, to quickly revise the conditions, it has to be constant diffusivity for constant density in compressible fluid, no reaction, the fluid is static, you don't have any bulk flow, and this is the shape of the equation in mass units and in molar units. The boundary conditions have to be as we see here. We have to have initial uniform concentration. So the initial condition is that the concentration anywhere in the system is constant, which is Ca node everywhere. And then we will have a constant concentration at one edge, which is the boundary condition. At time greater than 0, the concentration here is always constant. So it's not a flux, it's not rate of reaction, it's always constant, and it's constant, as we said, along the whole distance here, or this whole side. And as the diffusion process proceeds, the concentration starts to increase or change, maybe increasing or decreasing depending on the direction of diffusion, but it's gonna change in this direction. And at time equals like very long time, then CA equals CE node everywhere. So this is what the conditions that we have. The boundary conditions start here at CA1, this is at CA node, and then diffusion will proceed. So these are the conditions of using the charts. If you have different boundary conditions or a different initial condition, then you cannot use the charts. So you have to make sure that these conditions are valid for the or these restrictions are valid for the boundary conditions, initial condition, and the equation itself. Now let's take a look at the parameters. So the parameters that we have are the time, the actual position where I want to get my concentration at, and at this time, of course. So these are the inputs that I want to provide to the relation that I have, the time and the location. We know some characteristic length that is function of the shape itself. It's the dimension of the shape, and we have the initial concentration, the surface concentration, which is the concentration at the surface at the boundary condition, and the CA, which is the output. So this is the main output that I want to get after performing the calculations or using the chart to get the concentration at this time and at this location. And now these are the parameters in the dimensional forms, the actual values. So back to the point that we mentioned, that the chart is a kind of relation. I provide the time, the location, or the position in dimensionless forms and get the concentration in a dimensionless form. So I expect the dimensionless parameters to be three. One for the concentration, one for the time, and one for the position. And this is what we see here. We have Y, which is the unaccomplished concentration change, HCAS minus CA divided by CAS minus CA node. The range of this Y or CA would be somewhere between CA node and CAS. This is the maximum minimum values. So Y would be somewhere between 0 and 1. So this is the range of Y. Here we have the XD, which is the relative time or the dimensionless time. It's D multiplied by T divided by X1, which is the characteristic length. And we have here N equals X divided by X1, so it's the position relative to the characteristic length. So these are the three parameters that we discussed, the position, the time, and the concentration. However, we have one more dimensionless parameter here, and this is one thing that we will discuss later. I'll keep this for now, but just for now we have these three dimensionless parameters. But here you'd see X1 and X1 here. It's not clear what is X1 and it's not clear what is X. It says characteristic length here and the actual position, and this is actually a function of the shape of the body or its geometry, and that's why we will talk about this in more details now. So if we want to discuss the geometries that we have, there is one more restriction that we didn't mention about the use of the charts, and this restriction is that it has to be for symmetric shapes. By this we mean that there is an axis of symmetry where the two sides around this axis of symmetry are mirror images. So whatever is on this side, above or below, like in this case, or right or left, like in this case, they are identical from the dimension point of view and from the concentration point of view as well. And this is a very important point. So the three shapes that we have, as we said before, is the slab, the cylinder, and the sphere. I'll discuss these three shapes first. So the definition of the characteristic length, which is X1, is the distance from the point of symmetry. So this is the distance from the point of symmetry to the outer edge of the body. So in this case, the slab has a width of L. And this is what I said here, the X1 distance from the midpoint to the surface from which the transfer occurs. So this is the axis of symmetry. This is the length L. So from the axis of symmetry or the midpoint of the surface to the outer surface, it is L over 2. So this is x1 here. The same for a cylinder. This is the axis of symmetry. The outer distance is r, so the x1 is r. The same for the sphere. X1 is r. So this is how I can get the value of x1. You'd see that x is somewhere between the midpoint or the axis of symmetry and x1. It's logical. So it's gonna be somewhere from 0 to x1. This is the value of x. And in this case, if I want to get the dimensionless distance, which is n, it's x over x1, so its range will be from 0 to 1 as well. So here in this case, the x1 is r, and n is r over r, the lowercase r divided by r. Lowercase r is any radius from 0 to r, the uppercase r, and the same for here. So for these three cases, or for all the charts that we have, the value of n is gonna be somewhere between 0 and 1. There is one more case which is not a symmetric case, but we can use the charts for, which is the case of flat plate that has impermeable barrier. So in this case, we have no diffusion in this direction, and diffusion is only taking place in one direction. It's in here. So what we can do is to assume or to imagine that there is another side where the diffusion is exactly like this side, which is exactly like this side. So we imagine that this is a half and there is another half in the bottom, and in this case the total length of this body is L. L multiplied by 2. It's L here and L here. And in this case, the x1 is gonna be equal to L. So this is not a real symmetry. It's an imaginary symmetry. So we can assume that this is half of a total shape, which has an imaginary other half, and this imaginary half has the same length. So the length of from the axis of symmetry. So this side now is the axis of symmetry, the surface here. It's the axis of symmetry. And from axis of symmetry to the surface is gonna be the value of x1, which is L. So these are the dimensionless parameters. So if we can go back here and check, so now we understand y, we understand xd, and we understand n. So we can calculate these two because we know how to get the value of x1 right now, and we know what is x, so we have no problem with these three dimensionless parameters. We need to talk about this to understand what is the point of having one more dimensionless parameters if I have already two inputs and one output. So this is going to be the topic of next video, inshallah. So I'll see you then.